Hello everyone, this is Fairuz Khan, and today I'm going to present my final project presentation on developing a healthcare cost predictor, a data science web application. So let's walk through what I'm going to cover today. We'll begin with data understanding, followed by exploratory data analysis. Next, we'll look at how I engineered the features, implemented several machine learning models, and finally demonstrate how I have built the Streamlit-based web application. So first, let's look into the dataset overview. The dataset includes 1,338 insurance records with 7 features like age, BMI, smoking status, and charges. Our target is the charges column. Each feature is carefully chosen to reflect lifestyle, demographics, and risk factors affecting medical costs. So here's the descriptive statistics summary. On average, individuals are found to be 39 years old with a BMI of around 30, which is technically considered overweight. The charges also vary dramatically from just over 1,000 to nearly 64,000. This wide range indicates significant impact from factors like smoking and age. Now let's look into some EDA distributions. First, we examined gender and number of children, and both are found to be fairly balanced, except for the children. Here we find that most of the people are without children. The histograms for charges, age, and also BMI that show that most people are kind of younger and charges are skewed towards the right. And also the BMI distribution is slightly high, and also the plot is kind of normal, indicating that most of the people are overweight here. The smokers make up to 20% of the data set, but have drastically higher charges as seen in the box plot. And next, we look into the average charges by age group, region, and also BMI category. We find that seniors and obese people, these people face higher costs, and regionally, the Southeast stands out with the most expensive healthcare. Now let's look into the correlation heat map, and we find that age has to be the strongest, has to have the strongest correlation with charges. BMI and the number of children show very weak correlations. In the pair plot, we find that smokers consistently have higher charges across all ages, and which highlights smoking as a major cost driver. So now to prepare for modeling, I used one-hot encoding for categorical features like gender, smoker, and region. This converts them into binary columns, removing any unintended rank or order, while preserving their meaning for machine learning. For numerical features like age and BMI, I apply standardization, scaling them to a mean of 0 and standard deviation of 1. This ensures each feature contributes equally, preventing models from being biased toward higher magnitude variables. We now move to machine learning. I started with linear regression, a simple model establishing a linear link between features and charges. The baseline model gave an R-square of 0.784 and root mean square error of around 5796. So here's the plot of the baseline model, actual versus predicted charges, and we see that they are kind of towards a linear trend, but kind of more scattered. Now, adding interaction terms like age into smoker, it improved the performance significantly to R-square of 0.866 and root mean square error of also reduced to 4567. Now, this is the plot with the interaction terms, and we see that the actual and predicted charges are now kind of comparatively more closer, towards the predicted line. Next, I used permutation importance to measure each feature's contribution by observing how shuffling them affects accuracy. So found out that smoker status and BMI, smoker and age stood out. I then created a simplified model using just these key features. And impressively, the smaller model achieved R-square of 0.854, and RMC was also like 756, which was almost as good as the full model. To improve the generalization, I tried ridge and lasso regression. So both added regularization and matched the best results with R square of 0.866. Then I tested ensemble models, random forest, and XG boost. These perform similarly and capturing complex interactions with low RMSE around 4500. And this all confirms that the ensemble methods handle this data very well. Now let's look into the model performance comparison charts. It summarizes the performance of all models, and we find out that Ridge, Lasso, and Random Forest consistently uh, led with R square near 0.866. Also, the model RMSE comparison also shows that these three have the lowest RMSE values. And the key drivers of insurance costs are found to be smoking, age, and BMI. Finally, I deployed the model in a Streamlit app that takes user inputs like age, gender, BMI, and smoking status, and predicts medical charges using the XGBoost model. So it displays results on a kind of dynamic gauge and provides personalized cost level feedback. The app is here shown in live, and when I click into it, we can see that it is fully interactive. So on the left, it has the navigation pane where we can go to different pages. The first page is about the data exploration. We explored the data and also look into the descriptive statistics. The second page is about the EDA, where we have all the plots, and some are static, some are also interactive, like the correlation heat map is interactive. The third page is about the feature engineering, which covers the one-hot encoding and standardization. The fourth page is about the machine learning models, where we have all the plots as well, which are also interactive. Also the feature importance plot. The final page is about the charges prediction. So if the customer kind of inputs his or her details like age, then also selects gender and the BMI status and their number of children, their smoking status, and where they come from. When they select this, they get their summary here. And if they're confirmed this thing is accurate, then they predict charges. And this is the final gauge that appears here. So yeah, and also they get a customized feedback based on that. The final page is about showing gratitude towards the Build Fellowship project under which we actually made this app, and special thanks to our mentor Ujjwal Gulabali. So that's all. This concludes my presentation, and thank you for your time. And I'm really happy to participate in this project. Thank you very much.